Hi guys, today we're going to go through quantitative chemistry. This is a revision lesson. It is something that we have gone over in a lot of detail, but I just want to highlight some key principles for this topic. It is quite a tricky one, but if you do have any questions, then please reach out to me on the specific areas that you're struggling with. I would advise that you pause the video, you make notes, you have a go at the practice questions, and you rewind the video in areas that you're finding difficult. Now, we're going to start by looking at the atom. Now, everything comes down to the atom in chemistry. When different types of atoms react, we form a variety of different products. Now, different types of atoms that exist are called elements. Now, we have a periodic table of elements, which are all of the known different types of atoms that exist. Now, the thing that makes one atom different to another type of atom, or one element different to another element, is its mass. Now, the mass of an atom comes from its nucleus. It's centered in the nucleus because the mass of the atom is a combination of the mass of the protons and the neutrons, and we call that number the mass number of an element. And we're going to be referring to that mass number as we do different calculations involving moles. Now, a key principle before we get on to moles is the conservation of mass. Now, this principle is basically saying that during a chemical reaction, the mass of our products equals the mass of the reactant. So I've got an example here of sodium reacting with chlorine, making sodium chloride. Let's say we've got 3 grams of sodium, 5 grams of chlorine. According to the law of conservation of mass, assuming that no atoms are lost, I will have 8 grams of sodium chloride. Now, balancing equations is a key skill for chemistry, guys. The idea is essentially that you have the same number of atoms on each side of the arrow. So, for example, if we look at this reaction here, on the left I've got 3 carbon atoms, but on the right there's only 1, so this equation is clearly not balanced. And what you have to do is you need to put numbers in front of every molecule until the number of atoms on each side is the same. And we won't be going into detail about how to balance equations for this video, but it is a key skill that you need to have when using mole calculations. Now, just something to make a note of, the law of conservation of mass says that mass is unchanged after a reaction. Now, it can appear sometimes that mass has increased or decreased, and that is with reactions that involve gases. For example, if you have a metal that reacts with oxygen, the metal will appear to have increased in mass. So reaction 1 in that picture is basically rusting. What happens is oxygen molecules react with the metal and they form metal oxides and the mass increases. In the second example, one of our products is a gas. It's thermal decomposition reaction. So when you heat up metal carbonates, you form a metal oxide and carbon dioxide gas. Now, with oxygen and carbon dioxide in both examples, they both are in the atmosphere, so it can be very difficult to measure their mass on, say, a balance, because all of the gas escapes into the atmosphere. So that is just something to make a note of, but the principle is always true, that you never lose mass, but it can appear that mass is lost in a reaction, or mass is gained. The relative formula mass of a compound is the sum of the relative atomic masses of the atoms in the numbers shown in the formula. Now, we've got here carbon as an example. Now, Carbon has a mass number of 12. But if carbon was bonded to, say, 2 oxygen atoms, we would have a carbon dioxide molecule. Now, I know the individual mass of carbon, but what would I do if I needed the mass of the whole molecule, carbon dioxide? Well, I would need to add up the individual masses of the atoms. So in carbon dioxide, I've got 1 carbon and 2 oxygens. So that would be 16 times 2 for the oxygen plus 12 to give me the mass of carbon dioxide. I wanted to use that as an example to have a go at these 4 questions here. And you do not need to use your periodic table because the relative atomic masses have been given in the question. So pause the video and have a go. And this is what you should have got. And well done if you've got those right. Okay, another key skill that you need to have is to be able to work out the percentage of an element within a compound, and you need to know this equation. Essentially, you do that by working out the MR of the compound, and whatever element is in question, you need to divide that by the MR of the compound and times it by 100. So for example, what is the percentage of sodium in sodium carbonate? So the first thing you need to do is work out the MR of sodium carbonate, then the mass of sodium in that compound, and then times that by 100. So you should have 23 times 2 because I've got 2 sodium atoms. Divide that by the MR of sodium carbonate, which is 106, times it by 100, that's 43%. So what that means is 43% of sodium carbonate is made up of sodium. Right, I want you to use that example to have a go at these questions. So just pause the video and have a go. Okay, moles. Now, chemical amounts are measured in moles. The symbol for moles is MOL or mole. The mass of 1 mole of a substance in grams is numerically equal to its relative formula mass. So I've got here on the right, 1 mole of anything is the MR in grams. 1 mole of a substance contains the same number of the stated particles, atoms, molecules or ions as any other substance. Now we know that that number is equivalent to 6.02 times 10 to the 23 molecules. We call that number Avogadro's constant. So let's look at what we've got here. We've got 1 mole of carbon is 12 grams. So you got to think, where's that 12 grams come from? Oh, I know the 12 grams is the mass number of carbon. The same with sodium. 23 is the mass number of sodium. Now carbon dioxide, CO2, has a MR of 44. So 1 mole of carbon dioxide is 44 grams. Now where does Avogadro's constant come into this? Well, I've got 1 mole of each of these substances. So that means that each of those substances contain 6.02 times 10 to the 23 molecules. So 1 mole of carbon, which is 12 grams of carbon, has 6.02 times 10 to the 23 molecules, whereas 44 grams of carbon dioxide has 6.02 times 10 to the 23 molecules. So that, guys, is a definition that you need to know. 1 mole of any substance has 6.02 times 10 to the 23 molecules, and 1 mole of any substance, if you want to know the mass of 1 mole of a substance, you just convert the MR into grams. Now, this is an exam question that I'd like you to try. Calculate the number of molecules in 14 grams of carbon dioxide. Give your answer in standard form. They've given us the relative atomic masses. Usually carbon has a mass of 12, but just make sure you notice that the carbon here has a mass of 14. It's an isotope. You need to use Avogadro's constant to calculate how many molecules there are. So just pause the video and have a go. And you should have got that there are 1.81 times 10 to the 23 molecules. Now the idea is, the first thing you should have done is worked out the MR for 46 grams. So in 46 grams, there are 6.02 times 10 to the 23 molecules. But they want to know how many molecules there are in 14 grams. So there's a variety of ways that you could have done it. I would have worked out how many molecules there are in 1 gram and then times that answer by 14, and you should have got 1.81, which is about a third of Avogadro's constant. Okay, so now you need to be able to calculate the mass of different substances within equations, and that is obviously within balanced chemical equations. Now you could be asked to calculate the mass of any reactant or any product in a chemical equation. You also need to be able to understand how to describe equations in terms of moles. So you've got an example here of magnesium reacting with hydrochloric acid. Now this is a balanced equation. Essentially it's showing that for every 1 mole of magnesium, 2 moles of hydrochloric acid are required to make 1 mole of magnesium chloride and 1 mole of hydrogen gas. Remember, in chemistry we don't write ones in front of our molecules, but this is a balanced equation. Now there is a formula that you need to know that relates mass in grams, MR and moles, and this is the equation. Moles equals mass divided by MR, or relative atomic mass. Just make sure you remember that the units for MR are grams per mole. Now we're going to go through this question together. It says calcium carbonate is decomposed by heating. The reaction produces calcium oxide and carbon dioxide gas. What mass of calcium dioxide is produced by 12 grams of calcium carbonate? So I've got here a balanced equation, and remember we said that we need to be able to calculate the mass of either products or reactants in a balanced equation. So first thing I'm going to check is my equation balanced? And the answer is yes, it is balanced. And then I've got to make sure I understand what the question is asking me to calculate. So they're saying that I've got 12 grams of calcium carbonate and I need to know the mass of calcium oxide. So actually what I can do is I can negate or not worry about the carbon dioxide, because that is not being asked of me in the question. Now I like to use this table method because I think it quite clearly lays out what information we know and what information we need to find out. So the first thing we're going to do is we're going to look at our ratio of moles. So like we said before, we need to be able to interpret chemical reactions in terms of moles. This equation shows that for every 1 mole of calcium carbonate, I'm making 1 mole of calcium oxide and 1 mole of carbon dioxide gas. So my ratio of molecules will be 1 to 1. Now I need to see what other information do I have. Do I have the mass? Well, I've got the mass of calcium carbonate, that's 12 grams, but I'm trying to work out the mass of calcium oxide, as that is what the question is asking me to do. I can work out the MR using the information provided. Calcium carbonate has an MR of 100, calcium oxide an MR of 56. Now using my triangle, I'm going to work out the moles of calcium carbonate. So moles is mass divided by MR, so do 12 divided by 100 is 0.12. Now because I don't have the mass of calcium oxide, I can't use my triangle for this second calculation, but because I know my ratio of molecules is 1 to 1, because I've got 1 mole of calcium carbonate, I'm also going to have 1 mole of calcium oxide. So if I've got 0.12 moles that I've calculated of calcium carbonate, I'm also going to have 0.12 moles of calcium oxide. So now I've got moles and MR. Can I work out mass? Yes, I can. Just rearrange my equation. Mass is moles times MR, and the answer is 6.7 grams. Right, I want you to pause the video and have a go at this question. I've helped you out a little bit by identifying what information we have and what information we're trying to work out. Okay, so the question is saying when aluminium is made, iron is made when aluminium reacts with iron oxide. This reaction is used to weld railway lines together. What mass of aluminium is needed to react with 640 grams of iron oxide? So essentially, I'm not interested in the products because the question is just asking me to work out how much aluminium I need for this reaction. Now I've been told that I've got 640 grams of iron oxide. If I look at my balance equation, it says that for every 1 mole of iron oxide, I need 2 moles of aluminium. So my ratio of molecules would be 1 to 2. I've got 640 grams, so I'm going to put that there, and I'm trying to work out the mass of aluminium. I'm going to work out the MR using the atomic masses given, and you should have got 160, and aluminium has an MR of 27. If I want to work out moles, I need to do mass divided by MR. That gives me 4 moles. So with that given mass, I've got 4 moles of iron oxide. Now, in order to work out the moles of aluminium, I need to look at my ratio of molecules. My ratio of molecules is 1 to 2, so I need to double the moles to give me 8 moles of aluminium. Now I'm going to rearrange my equation to find mass. 8 moles times 27 is 216 grams. Okay, now we've been using balanced equations to find the masses of different substances. Now we're going to go the other way around. We've got to work out how to balance equations when being given the masses of all the reactants and all of the products. Okay, and you need to be able to do that by firstly being able to write out chemical equations, identifying the masses of those reactants and products, then working out the mole ratio. So you're going to need to do that by working out the MR, and then what we need to do is find the simplest whole number ratio. So remember, when you balance equations, we use whole numbers, we don't use fractions, so we need to convert our mole ratios to the nearest whole number. So let's do an example together. We've got here, it says when copper metal reacts with oxygen, black copper oxide is formed. So they've essentially described a reaction to us. So then first thing we need to do is write out the equation. If it helps, write out the word equation first, like I've done, and then write the symbol equation. So copper plus oxygen makes copper oxide. Now in the experiment it says that the copper reacted completely with oxygen. 6.35 grams of copper reacted with 1.6 grams of oxygen and 7.95 grams of copper oxide was formed. So I'm going to fill my boxes in for all of those substances. Now I'm going to use my periodic table to work out the MR. So copper has an MR of 63.5. Oxygen, remember guys, is a diatomic molecule, so we need to do 16 times 2. Copper oxide has an MR of 79.5. To work out the moles, you do mass divided by MR, 0.1, 0.05 and 0.1 again. Now, in order to find the simplest whole number ratio, I need to divide by my moles by the smallest value. So of the moles calculated, the smallest value is 0.05. So I'm going to divide all of those moles by 0.05, and that's going to give me 2, because 0.1 divided by 0.05 is 2, 0.5 divided by 0.5 is 1, 0.1 divided by 0.05 is 2 again. So if I then wanted to balance my equation, I'm going to use my ratio of molecules and put those numbers in front of my symbol equation. So 2 molecules of copper, or 2 moles of copper, react with 1 mole of oxygen to form 2 moles of copper oxide. Now remember, we don't write the ones when we're balancing equations, so that's why I've not written anything there. So essentially that would be your final answer. Okay, limiting reactants. Now, in a chemical reaction, whenever you've got a chemical reaction, one of the reactants will be in excess, i.e. you'll have more than what is needed, and because of that, one of the reactants there won't be enough of, because it will get used up first. And we use the term excess or limiting to describe those reactants, and you need to be able to identify if the reactant is in excess or if it's limiting. The idea is, if the reactant gets used up first, then that reactant is limiting. So let's think of an example here. So you've done this one before, magnesium ribbon in acid. Now, we know that this reaction produces bubbles. It's an exothermic reaction as well. Now, the bubbles rise to the top. And we know that the reaction is over when the bubbles disappear. That indicates that the reaction is no longer happening. Now, if there is still magnesium ribbon in the test tube after there's no more bubbles being produced, i.e. once the reaction is over, what reagent or what reactant is limiting and what is in excess? So just have a pause of the video and think about that. Okay, so if the reaction is over and I've still got magnesium in the test tube, that tells me that hydrochloric acid is limiting, as in all the acid particles have reacted. So there's not enough acid left to react with the rest of that magnesium ribbon. So we would say that the acid is limiting and the magnesium is in excess. Right, scenario 2. What if the magnesium completely disappears and it looks like it's just dissolved in the acid once the reaction is over? What does that indicate? Pause the video again and have a think. Okay, so the idea is that the magnesium is limiting, so it's the opposite scenario. It got used up first, and if you put another ribbon inside of it, it would start bubbling up again. So whatever runs out first, whatever finishes first, is the limiting reactant. Now you need to be able to identify the limiting reactant when you're given the masses of all of the reactants. So in this example, we've got 4.8 grams of magnesium and 7.3 grams of hydrochloric acid. So the first thing you need to do is write out the balanced chemical equation. So you need to make sure that it is balanced according to the law of conservation of mass. Now, according to the balanced equation, for every 1 mole of magnesium, I need 2 moles of hydrochloric acid. So that is what we know. Now, according to the measurements that we've been given, we need to identify, in this case, in this reaction with 4.8 grams of magnesium and 7.3 grams of hydrochloric acid, which reactant is limiting. Which one's going to run out first? So we've got our equation. The next thing we need to do is identify the known masses of only the reactants. We don't need to worry about products because remember we're finding the limiting reactant, and we're going to work out the moles based on the masses that we've got. Now, if we've got 4.8 grams of magnesium and 7.3 grams of hydrochloric acid, so divide the two by the MR, that would give us 0.2 moles of magnesium and 0.2 moles of hydrochloric acid. Now we need to look at the ratio of the balanced equation. Now from my balanced equation, it says that for every 1 mole of magnesium, I need 2 moles of hydrochloric acid. But my calculations have told me that essentially my ratio is 1:1 in that reaction. So I've got 0.2 moles of magnesium and 0.2 moles of hydrochloric acid, when actually I need 0.4 moles of hydrochloric acid. Now, because there isn't enough hydrochloric acid, we can say that hydrochloric acid is a limiting reactant and that magnesium is in excess. So what that means is not all of the magnesium will react in this reaction because there's not enough acid particles. I want to use the same steps. If you need to go back to the previous example, then rewind the video, but I want to have a go at this question. So we've got aluminium reacts with iron oxide. So we've got aluminium, Al plus Fe2O3 makes Al2O3. So you need to firstly write out that equation. If it helps, write the word equation first, then write the symbol equation, make sure it's balanced. Write down the masses of the reactants underneath it. Write down the MR of the reactants. Work out the moles. Then look at your mole ratio and compare it to the balanced symbol equation. Out of the two, which one will get used up first, aluminium or iron oxide? Pause the video and have a go. So the first thing you should have done is written out the balanced equation, and according to the law of conservation of mass, 2 moles of aluminium are needed to react with 1 mole of iron oxide to make 1 mole of aluminium oxide and 2 moles of iron. Now, to identify the limiting reactant, you need to work out the moles of the reactants with the masses that you've been given. So you should have calculated that we have 0.6 moles of aluminium and 0.2 moles of iron oxide. Now, from the balanced chemical equation, because the ratio of molecules is 2:1, I actually need 0.3 moles of iron oxide, not 0.2. That tells me that iron oxide is going to run out before the aluminium, okay? And therefore, because this will get used up first, because I don't have enough of it, I need 0.3 moles because my ratio is 2:1. We need 0.3 moles to completely react with 0.6 moles of aluminium. Therefore, aluminium is in excess and iron oxide is the limiting reactant. Now, this next question, part C, we didn't do an example together, but we're going to talk through it now. It says calculate the maximum mass of iron that could be collected at the end of this experiment. So we're now going to be looking at the product side. We're talking about iron. Now, our ratio of molecules of iron oxide to iron is 1:2. Now, in order to work this out, I need to use the moles of the limiting reactant. The moles of the limiting reactant is 0.2. So this is 0.2, and my ratio of this is 1:2. Right, okay. So if I've got 0.2 moles of iron oxide, I'm going to need 0.4 moles of iron. Therefore, the mass of iron produced is going to be 0.4 times 56, which gives 22.4 grams of iron produced with this mass of iron oxide initially. Okay, now the last thing we're going to look at is concentration. Now, many chemical reactions take place in solution. The concentration of a solution can be measured in mass per given volume. Okay, so that is a definition of concentration, and there's many different ways of writing concentration. We usually use grams per decimeter or moles per decimeter. You need to understand these conversions. 1 litre is the same as 1,000 centimetres cubed, which is the same as 1,000 millilitres, which is the same as 1 decimetre cubed. Okay, so when you're doing these sorts of calculations, you need to be really careful to check what units they have asked for. Now, it says here the concentration of sodium hydroxide is 12 grams per decimetre cubed. What does that mean? It means that 12 grams of sodium hydroxide has been dissolved in 1 decimetre cubed of water. So those units are giving us a lot of information. They're telling us that 12 grams of these sodium hydroxide particles are dissolved in 1 decimetre cubed or 1,000 centimetres cubed of water to make this solution up. Now, the equation for concentration is mass divided by volume. You could have worked that out just by the units for concentration, so just make a note of that formula. And just something else to think about, if you wanted to increase the concentration of any solution, you would need a higher mass to volume ratio. So you can increase the mass of the solute by adding more solute particles and dissolving more in the same volume of solution, or you could evaporate some of that water off to give you a more concentrated solution. Now, the last thing I'd like you to do is have a go at calculating the concentration of these different solutions. We'll do the first one together, and then you can pause the video and have a go at the others. So I want you to work out concentration for 2 different units, grams per decimetre cubed and moles per decimetre cubed. So for grams per decimetre cubed, it's nice and straightforward. We've got 3.65 grams of hydrochloric acid in 1,000 centimetres cubed solution. So I'm just going to do mass divided by volume. 1,000 centimetres cubed is 1 decimetre cubed. So 3.65 divided by 1 is 3.65 grams per decimetre cubed. Now, if I wanted to change that into moles, I need to think about what equation do I know that links moles and grams. Right, it's this equation, isn't it? Grams, moles and mR. So in order to convert my grams per decimetre into moles per decimetre, I need to know the mR of my solution. Okay, now therefore I need to work out the mR for each of these solutions. In this case, hydrochloric acid has an mR of 36.5. Moles is mass divided by mR, so I'm going to take my units in mass, grams per decimetre cubed, divide that by 36.5, and that gives me 0.1 moles per decimetre cubed. So there's 2 ways of writing out units. You can have it in grams per decimetre or moles per decimetre. So guys, that was a quick summary of this entire topic, and I've tried to do that just in one video. Of course, you can pause and go back to the different sections, and if you've got any questions about any of the subtopics, then just drop me a message.